All right, moving on to section 6.3. So section 6.3, we did implicit differentiation. So 6.3, we've got implicit differentiation. Again, we gave this one the friend's title. This was the one with dy dx. Okay. How will you know that you're supposed to use implicit differentiation, right? In 9.2, we learn about doing partial derivatives. How do we know that we need to do implicit differentiations? So what you'll see to tip you off to this fact is that you'll see that we have an equation with both x's and y's, or I should say with x's and y's on both, there we go, sides of the equal sign. Okay. Really what I mean is not f of x comma y. This guy, again, is a 9.2 problem. Okay, again, this guy right here is a multivariable function. We just want something with x's and y's on both sides of the equal sign. You could have a number on one side. That's also fine. I'll take care of that case in an example. Let's talk about how we find these things. So step one, we're going to take the derivative in a slightly different way of, we're taking the derivative of both sides of our equation. We're going to take the derivative of both x and y at the same time. And so here, hot tip, remember to use the product rule. This kind of was a big contributor in this section. But the main trick here that was different from just normal differentiation is whenever you take the derivative of a y term, you need to multiply by dy dx. Okay, and then step two, we're going to solve for dy dx. Solve for dy dx. And then again, our little process for this guy was to move all of our dy dx terms to the left, all non-dy dx terms to the right. We'll then factor out a dy dx on the left and divide. And then one of the main things that we did here was that using this, we can find the slope of the tangent line. This is a big, important idea that has come up on every single exam. I will say it, I've said it once, I'll say it again. It would behoove you to understand how to find the equation of a tangent line. right? dy dx is going to be the slope of that line, and then we just need a point. Okay, all right, now let me do an example of implicit differentiation stuff. This one will probably be rather quick, and I won't do one that's on the review. I'll just come up with one right now. So an example, we see that I have something like x squared y cubed plus e to the y plus x to the fourth equals 13. Okay, again, something to notice. This guy is defined implicitly. I can't separate out my x's and y's. I can't solve for y. That's not a thing that I can possibly do. I still want to take the derivative. Also notice there's no f of x comma y. That's not happening here. I have a 13 on this side. That's okay. So I'm going to use implicit differentiation. Here in this first step is one case where I'm going to use the product rule. I have a product of two things. Okay, so the derivative of the first is 2x times the second is y cubed plus the derivative of the second, 3y squared dy dx times the first. Again, this guy was just the derivative of my first term. All right, plus the derivative of e to the y is just e to the y dy dx, plus the derivative of x to the fourth is 4x cubed. No dy dx, I just took the derivative of an x term, so it's fine. This guy's going to equal the derivative of 13 is just 0. Okay, now everything that doesn't have, or everything that does have, I'll say it in the affirmative first, everything that does have a dy dx stays on the left. Everything that does not moves to the right. So this begins to look like, I'm going to reorder this term a little bit, so it looks like 3x squared y squared dy dx plus e to the y dy dx equals negative 4x cubed minus 2x y cubed. Okay, I'm going to factor out my dy dx over here. Dy dx times 3x squared y squared plus e to the y equals negative 4x cubed minus 2x y cubed all over 3x squared y squared plus e to the y. Okay, or I got ahead of myself, sorry guys. So I already divided. So I have dy dx times this guy. I just factored out the left hand side. I'm going to leave the right hand side as it is. Now I'm going to do that division. Dy dx equals negative 4x cubed minus 2x y cubed all over 3x squared y squared plus e to the y. And again, these little guys up here are y's. All right, so that's implicit differentiation. I found this guy. Now if I wanted to find the equation of tangent line through, oh geez, let's say the fourth root of 12, comma 0. Again, this example is like pretty contrived. So if I wanted to find the equation of the tangent line through this guy, what I would do is I'd just plug it in here. It's going to turn out ugly. I shouldn't. This is why you don't make up problems on the spot. But I know that dy dx equals negative 4 times the fourth root of 12 cubed minus 0 all over 0 plus 1, which is just negative 4 times. This is going to, I'll rewrite it as 12 to the 3 over 4. Again, you can mess with this and manipulate it to simplify it, but this is all just divided by 1. So for the equation of my tangent line, I have a point. I have my slope. So I'm good to go. I know that I can say that y minus 0 equals negative 4 times 12 to the 3/4 times x minus the fourth root of 12. Now again, if I were doing this on something like an exam, it wouldn't be a weird point like this. I know that this kind of 4th root of 12 thing would likely throw some of you guys off. Don't worry, it will work out nicely, but I needed this point to work in my original equation. Okay, so again, don't worry about there being something so contrived as the 4th root of 12, but this is, again, how it would work. I wanted to show you that extra step. All right, so we found the equation of the tangent line, a thing that we've done on every single exam. It would be surprising almost if it didn't come up, but that's just me, the person who's written the exam. All right,